Okay, now let's look at some examples in this section for inverse trig antiderivatives or integrals. And so let's just start out with a couple pre-selected from the book here. First one, we have the antiderivative of dx over 4x times the square root of x squared minus 16. So what we really want to do is we want to try and rewrite this in terms of something that looks like one of the three base inverse trig antiderivative functions that we have. So it looks like it's going to be kind of similar to that arcsecant one that we had as well. So let's see if we can rewrite this. First of all, that 4, I don't really like that down in the denominator there, so I want to try and pull that out front. Of course, that is a fraction. It's in the denominator, so it'd be 1/4 the antiderivative of dx over, and now we just have x times the square root of x squared minus, it'd be nice if we had minus a squared. And so what is a here? A would be 4. So x squared minus 4 squared. Of course, a needs to be greater than 0 for the arcsecant antiderivative here. So anyway, this is going to end up being 1/4. And then that's the coefficient out front. And then this is set up exactly in the way that we can do the arcsecant antiderivative here. So this is going to be, remember, it's 1/4, 1 over a would be 1/4. That's from this 4. This 1/4 is out front here. But the antiderivative of this part right here is going to be 1/4 inverse secant of x over 4. And then I'm going to say, since this is all in brackets here, I'm going to say plus C1, just some particular constant. I'll call it C1. But then what I can do is I can multiply that 1/4 through there. And I'm going to say that, hey, this is equivalent to 1/16 the arcsecant of x over 4 plus C. So that would be our final antiderivative there. And of course, what can we do with an antiderivative? Once we take it, we could take the derivative of that and make sure you get exactly what's in here. Or if it's not exercised, we could check the answer in the back of the book and just do it that way. So I did verify this before I started the video lesson. This would be the correct answer here. So 1/16 arcsecant of x over 4 plus C would be the antiderivative of this. So let's go to the next one. Looks a little more awkward. We've got the antiderivative of e to the x over 7 plus e to the 2x with respect to x. So in this case, you know, back in Calc 1, you probably would have tried to do substitution, things like that. I think we're going to need to do that here. But since it's in the section of inverse trig antiderivatives, we want to try and make that look like one of them. Of course, the one that it might look like is arctangent. So let's try and rewrite this a little bit differently. And if we do that, we're going to have the antiderivative of e to the x. And then really what arctangent is, we got a squared plus x squared, right? Well, we don't have an x down here, but we do have an e to the x. So I could rewrite that as the square root of 7 quantity squared plus e to the 2x is really nothing more than e to the x quantity squared, and then with respect to x. So kind of the amen rule there, e to the x quantity squared is e to the 2x. So we're trying to rewrite it in a way that might look a little bit closer to what the arctangent antiderivative for arctangent ends up being. So let's try and look at this. Of course, it really doesn't look like that. So what are we going to do now? What I might want to do is I prefer that to be just like an x squared or a u squared. Since we already have x, what we can do is use substitution. So we're going to let u equal e to the x. And of course, that means du equals the derivative of e to the x is e to the x dx. So du dx, of course, moving that over here. And then what we can do is instead of e to the x dx, we can simply substitute in du. So this is going to be equivalent to the antiderivative of du on top instead of e to the x dx, right? And then on the bottom, it's the square root of 7 quantity squared plus u squared. And then this is definitely the form that's needed for the inverse tangent or arctangent function. So once again, for this, we need that a would not equal 0. For arcsecant 1 up here, we needed a to be greater than 0, which it was. For arcsine, we need a is greater than 0. But for arctangent, we just need to make sure that a here is not equal to 0 for reasons that we've already talked about. But anyway, so I can go ahead and say what this is. It is 1 over root 7. So 1 over a would be 1 over root 7 arctangent of, instead of x, it's u's here, so it'd be u over root 7 and then plus c, right? And then, of course, what do we do now? Now we're going to back substitute that because we let u equal e to the x. So with back substitution, this is going to be equivalent to 1 over root 7 arctangent of, instead of u, it's going to be e to the x over root 7 and then plus c. So that we made it look like a form, instead of this, we made it look like a form that we could actually recognize as the antiderivative would be arctangent there. So now the question had came up before, do we have to, is it okay to leave a square root of 7 in the denominator? The answer is absolutely. The only time we really have to rationalize the denominators if we're trying to find a limit or something of the nature. But if you'd rather multiply top and bottom by square root of 7 over 7 and square root of 7 over square root of 7, then it'd be square root of 7 over 7 there. Same thing here, but then attached to an e to the x. I'm not going to do this. This is just fine. This is good enough for me. So I'm going to go ahead and leave that root 7 in those denominators there. Okay, so hopefully that makes sense. So here's a couple here that we had, and then we have one more similar to one that we did in class. But anyway, this is the antiderivative of dx over the square root of 15 plus 2x minus x squared. Well, it would be great if this factored out, but it doesn't factor real well. It's, you know, I guess 5 minus x times 3 plus x, and it's not the square root of something quantity squared, so that doesn't really help us out. So since it's in the section dealing with inverse trig antiderivatives, why don't we try and make it look like something of that nature? And of course, when we had the integral of dx, one that we have is, if we have the integral of, I'll call it du over the square root of a squared minus u squared. If we had something like that, what's this? This is arcsine of u over a plus c, right? So we had this as one of our theorems. Of course, this is true if a is greater than 0. Remember, this one does not have the 1 over a factor in front. We actually proved that in class. But anyway, so we want to try and make this look like this. And the question is, how do we do that? Well, we're going to do a process of completing the square here. So what we really want to do is work with the denominator here and say, okay, how are we going to work with 15 plus 2x minus x squared and make it to be some constant squared minus something else squared? So we're going to rewrite this as the dx can be on top and on the bottom, and I'm going to leave a little space. I'm going to leave the 15 by itself. That's my constant. And then what I can do is, instead of x squared being at the end and having a minus sign there, remember this is a minus sign here. I'm going to pull that minus sign out front. And then what would I be left with? I'd be left with a positive x squared, because if I distribute that minus sign, it'd be minus x squared. And instead of plus 2x, I'm going to need minus 2x here in there. So I can rewrite this a little bit differently as the integral of dx over the root of 15 minus the quantity x squared minus 2x. And then, of course, here, what I can do is I can complete the square. So how do we complete the square? Whatever half of the coefficient that's attached to the x, we take half of that coefficient, which would be minus 1, and then we square it. And so minus 1 quantity squared is plus 1, so I'm going to add plus 1 there. And then what that allows me to do is whatever half of that coefficient was -1, I could rewrite this as x minus 1 quantity squared. And that ends up being x squared minus 2x plus 1. So the key to completing the square is if you're putting it in descending order and you have positive coefficient for the x squared anyway, take half of that coefficient and square it. So in this case, it's x minus 1 quantity squared. But what did I end up doing? I added 1 inside of there, which is really like subtracting 1 because I'm subtracting this whole quantity, right? So to make it equivalent, and since I basically put in there where I'm subtracting 1, to make it equivalent, I'm also going to have to add 1. And I'm going to do that on the constant here. So that's 15 plus 1. So that's 16. So now I can rewrite this as 16 minus x squared minus 1. Or let's just go ahead and rewrite what this is equivalent to. This is equivalent to the antiderivative with respect to x of the square root. Instead of 16, I can write that as 4 squared and then minus x minus 1 quantity squared. So now we're getting where it looks very close to this theorem that we had here, but instead of u, we have an x minus 1. So what we can do here is we can use substitution, and we can say, hey, let's let u equal x minus 1. So if I do that, let u equal x minus 1, what's du equal? Du equals dx. Okay, so this really becomes equivalent to the antiderivative of du over the square root of 4 squared minus u squared, which is exactly what this looks like. So using the theorem here, this is going to be, remember there's no 1 over 4 coefficient here, so it's just the arc sine of u over 4 plus c. Now, but that's not the final answer because what was our original problem? Our original problem had x's in it, right? So I need to back substitute this one. And when I back substitute that one, I'll come over here since we're running out of room there. But this is equivalent with back substitution to arc sine of, instead of u, it's x minus 1 over 4 and then plus c. So that would be the answer to this antiderivative here. So once again, trying to make something that looks a little bit awkward algebraically look like one of the theorems, the 3 main theorems that we had for these. Now, if you prefer, if your eyes get confused by that, go ahead and put parentheses around the x minus 1 over 4 because that's what we're taking the arc sine of. But those are really redundant parentheses, so we don't have to do that. So I'm going to go ahead and stop here. Clean up the board a little bit, and then I'm actually going to prove one of those 3 major antiderivative theorems for an inverse trig function, and I'll do that on the next video.